Okay, let's talk about transformers. For a long time, RNN were the go-to for handling sequences like text or audio. They process things step by step, remembering what came before. However, RNN had a big problem. They could forget earlier parts of a long sequence. CNN tried to tackle this with local filters, but didn't really understand relationships between words in the entire sentence. Transformers completely flipped the script. They use something called attention. Basically, every word looks at every other asterisk word and figures out how important it is. This allows them to handle long sequences much more effectively, and because they don't process things sequentially, they can train much faster. Okay, let's dive into self-attention. It's a really crucial part of how transformers work. Think of it like this. Traditional models read sentences one word at a time, which can be slow and make it hard to grasp long-range relationships. Self-attention lets the model look at everything in the sentence simultaneously. It does this by creating three vectors: a query, a key, and a value for each word. It then compares these queries to the keys of all other words to figure out how relevant they are. Finally, it combines the values based on these relevant scores. This creates a new representation that takes into account all the context around each word. It's like giving the model a really good sense of what's going on in the entire sentence. Okay, let's dive into how a transformer block actually works. The heart of these powerful models is the self-attention mechanism. Think of it as a way for the model to really focus on the most important parts of an input sequence. Instead of just processing things sequentially like older models, it considers all elements simultaneously and assigns them different levels of importance. To make this process even better, we use multi-head attention, which means we run several self-attention mechanisms in parallel, each looking at the data from a slightly different angle. Then, after the attention layer, there's a feed-forward network that processes the information further. Finally, residual connections and layer normalization help keep everything stable during training, crucial for building these huge models. Okay, let's talk about the difference between these two transformer types. Encoder-decoder transformers are like having a dedicated reader and a skill translate. They deeply understand the input and then create a new output based on that understanding. Think of them as being perfect for tasks where you need to transform one sequence into another, like translating languages. On the other hand, models like GPT, which we often hear about, are just incredibly good at generating text. They are essentially predicting what comes next in a sequence, building upon what they've already seen. It's like they have an amazing imagination and can keep writing without needing specific instructions for every step. Okay, so transformers are really clever because they process everything at once way faster than older models. But here's a key thing: they don't automatically know the order of words in a sentence. That's where positional encoding comes in. It's like giving each word a little tag that says, "I'm here at this position in the sequence." We do this using sine and cosine waves, creating unique patterns for every single spot. This lets the model learn how important it is for words to be in certain places. Basically, without positional encoding, the model would treat dog bites man and man bites dog as identical, a big no-no for understanding language. Let's talk about mass self-attention. It's a really important part of how these powerful language models, like GPT, actually work. Imagine trying to write a story one word at a time. You wouldn't want the model to see what it's going to write later, would you? Traditional attention mechanisms let the model see everything ahead of time, which isn't ideal for building text step by step. Mass self-attention solves this problem by only allowing each word to pay attention to words that came asterisk before asterisk it in the sequence. It's like a little blindfold. It focuses on the past, ensuring the model generates text logically and coherently, one word at a time. Okay, let's dive into how transformers actually understand language. A key component is multi-head attention. It's like giving the model multiple sets of eyes to look at the same sentence. First, each word gets converted into a vector representation. Then, we create three different versions of those vectors: queries, keys, and values. Think of the query as, "What am I looking for?" The key is, "What do you offer?" And the value is the actual content. The model then calculates how relevant each key is to each query using something called scale.product attention. This gives us a score showing how much focus each word deserves. We use these scores to weigh the values, creating a context-rich representation of each word based on its relationships with others in the sentence. And it does all this asterisk in parallel asterisk through multiple heads, allowing for a deeper understanding and capturing more subtle connections than simpler approaches. Okay, let's talk about layer normalization in transformers. It's a really important part of how these models work. Basically, LN helps to stabilize training. Imagine you're building a massive tower of layers, and each layer's activations can get super big or tiny, which makes things really unstable. Layer normalization tackles this by normalizing the values within each layer, ensuring they have a consistent scale, like making sure everything is centered around 0 with equal spread. It's applied right after the attention mechanisms and feed-forward networks in the transformer block, and it's what allows these huge models to train effectively. Okay, let's talk about a really clever trick that makes transformers so effective: residual connections. Think of these layers in a transformer like a long chain of processing steps. Without them, each layer would have to learn asterisk everything asterisk from the input. It's a huge amount of work. Residual connections are essentially shortcuts. They allow information to flow more easily through the network, even if one layer isn't performing as well. Each layer learns only the residual or incremental change needed, and that change is then added back in along with its own transformation. It's like building a skyscraper. You don't have to rebuild everything from scratch at each step, you just add on the new parts. Let's talk about what makes GPT tick. The core of these models is a transformer architecture. It's a really clever design that ditches the traditional sequential processing used in older methods. Instead, it uses something called multi-head attention, which allows the model to focus on different parts of the input at the same time, picking up on complex relationships between words. It's like having multiple lenses looking at the sentence. And crucially, GPT is only a decoder. It doesn't need an encoder. It's trained with a very straightforward goal: predict the next word in a sequence. Basically, you give it some text and it tries to guess what comes next, constantly adjusting itself based on whether it was right or wrong. This process of predicting the next token is how GPT learns all its amazing language skills from huge amounts of text data. Okay, let's talk about how the GPT models have evolved. Starting with GPT-2, it was a relatively smaller model with just 1.5 billion parameters, great for generating text, but sometimes a bit repetitive or nonsensical. Then came GPT-3, which exploded in size to 175 billion parameters. This massive increase led to better understanding and generation abilities, particularly the ability to learn from very few examples. Next up was GPT-3.5, where they really focused on aligning the model's responses with what humans want, using something called reinforcement learning from human feedback. That resulted in a huge improvement in instruction following. And finally, we have GPT-4, which is even bigger and more powerful. It can now handle images alongside text, has a much longer context window, meaning it can remember more of the conversation, and shows improved reasoning skills overall. Okay, let's talk about how Claude and GPT models differ. Both are amazing LLM, but they've been built with slightly different philosophies. GPT is essentially a super advanced autocomplete system. It predicts the next word based only on what came before. It's fantastic at creative writing and following specific instructions. Claude, on the other hand, uses something called retrieval-augmented generation, meaning it first pulls in relevant information from a knowledge base to help shape its response. Plus, it's guided by a constitution, a set of principles designed to make it more helpful, truthful, and safe. That's why Claude tends to be less prone to making things up. It has better grounding in factual information, especially when tackling complicated questions. Okay, let's dive into LLMA. It's a family of large language models created by Meta AI, and what's really cool about it is that it's designed mostly for research. Unlike GPT or Claude, which are kept under wraps, LLMA has been released with a community license, meaning researchers can actually download the models and tinker with them. It comes in different sizes, some smaller, making it easier to work with if you don't have massive computing power. Now, let's look at how it compares to other big players like GPT-4 or Claude 3. We see here a quick table summarizing the main differences. GPT-4 and Claude 3 are proprietary models, meaning only OpenAI and Anthropic control them, while LLM is open access, perfect for researchers exploring all sorts of possibilities. Essentially, LLM openness is driving a lot of exciting innovation in the field. Okay, let's dive into how GPT actually understands what it's writing. A core concept here is called causal attention, and it's really the secret sauce behind its impressive text generation. Unlike standard attention mechanisms that look at everything all at once, causal attention focuses on a single direction backwards. Imagine you're reading a sentence. You naturally remember what came before to understand the current word. GPT does something similar. It creates key vectors for each word and compares them against key vectors representing all the words that have come asterisk before asterisk it. The result is attention weights, telling us how much influence each past word has on the current one. But here's the critical part. These weights are only based on previous information, now peeking into the future. This unidirectional approach ensures GPT can accurately rely on its memory of what's already been generated when predicting the next word. Okay, so let's talk about the feed-forward network for FFNs inside transformers. These are like mini MLP that sit within each transformer block. They take a single token's representation, basically its embedding, and transform it through two linear layers, with a ReLU activation in between. The first layer expands the dimension, usually making it 4 times larger than the original, and then the second layer compresses it back down to match. Essentially, they add some crucial nonlinearity to help the model understand relationships between words in a more complex way. They're super important for capturing nuance, meaning, and generating good text. Okay, let's talk about how text gets fed into these massive AI models. It starts with something called tokenization, essentially chopping up the text into smaller pieces that the model can understand. There are a few different ways to do this, like byte pair encoding and sentence piece. BPE starts by treating individual characters as tokens and then combines the most common pairs over and over again. Sentence piece takes a slightly different approach, looking at the whole Unicode character set. The size of the vocabulary, basically the number of unique tokens the model recognizes, is really important. A huge vocabulary can capture more detail, but it also requires a lot of memory and takes longer to train. And if the tokenizer isn't good at handling words it's never seen before, those out of vocabulary words, that can seriously hurt performance. Subword tokenization methods like BPE and sentence piece are really clever because they strike a balance between all these factors, allowing models to handle both common and rare words pretty well. Okay, let's talk about something really important when it comes to these huge language models, their memory, specifically what we call the context window. Basically, this is how much of the conversation or document an LLM can actually remember and consider at any given time. A bigger window means the model has a better grasp of everything you've been discussing, leading to more accurate and relevant responses. However, increasing that window comes with a big cost. It requires significantly more computing power, making these models slower and more expensive to run. Okay, so language models aren't just guessing the next word. They're actually figuring out how likely each possible word is to come after what we've already written. Think of it like a really sophisticated prediction engine. Early models used things called n-grams, basically counting how often sequences of words appear together. But modern LLM, like GPT and others, use transformers with something called attention. Attention lets the model focus on the relevant parts of the input sequence when making its prediction, not just the last few words. This is a huge improvement. After the model calculates scores for each possible word, it uses a function called softmax to turn those scores into probabilities, so you get a nice, tidy distribution where all the probabilities add up to 1. Okay, so let's talk about how we actually make these incredibly powerful AI models useful for specific jobs. First, there's pre-training. That's where the model gets its general knowledge base, like a really comprehensive education in language. It's trained on an enormous amount of text from all over the internet and learns to predict what words come next. It's a huge undertaking. Then comes fine-tuning. Instead of starting completely fresh, we take that already smart model after all its general learning is done and give it targeted training on a smaller dataset related exactly to what you want it to do. It's like taking a brilliant student and specializing them for a particular subject. So pre-training builds the foundation, fine-tuning adapts it. Okay, let's talk about instruction tuning. You've probably heard amazing things about LLM like GPT. They can write stories, answer questions, even code. But sometimes, they don't quite follow what you ask of them, or worse, they might give you some pretty wild and inaccurate answers. Instruction tuning is a really clever way to fix that. It's basically like giving the model a detailed training manual on how to respond correctly to different types of prompts. We feed it tons of examples showing exactly how to follow instructions, summarize this article, translate the sentence, you name it. And the great thing is, by focusing on instruction following, we see huge improvements in accuracy and reliability, making these models much more helpful and safer to use. Okay, so one of the key reasons ChatGPT is so impressive is this technique called reinforcement learning from human feedback, or RLHF. Initially, these large language models are really good at just predicting what comes next in a sentence, almost like a super advanced autocomplete. However, that doesn't always mean they give you helpful or even safe answers. To fix this, OpenAI used a process similar to training a dog. First, the model is trained on examples of questions and great answers. Then humans rate different responses to the same question, telling which answer was better. This rating data is used to train another AI called a reward model that learns what humans consider good quality. Finally, the original language model uses reinforcement learning, guided by this reward model, to generate responses that are more likely to get high scores from the human-trained reward system. It's a complex process, but it's what really allows ChatGPT to sound so conversational and aligned with our expectations. Okay, let's talk about how Mistral 7b is a game-changer in the world of large language models. Earlier LLMA versions were incredibly impressive, but they were huge asterisk. Like, really huge, especially the 65 billion parameter version. That meant training and using them was super expensive and slow. Mistral 7b changes all that. It delivers performance nearly as good as a much larger LLMA model, but with only about half the parameters. How did it do that? Well, Mistral uses clever tricks like grouped query attention. Think of it like streamlining how the model focuses on different parts of the text and sliding window attention, which limits how far each token can look at other tokens. It's all about making things faster and more efficient without sacrificing quality. Okay, so when we want to teach an enormous LLM like GPT or Claude how to do something specific, maybe write poetry in a certain style or answer questions about a niche topic, we usually have to fine-tune the entire asterisk model. That's super resource intensive and requires a lot of computing power. LoRA changes that game completely. It's like this: instead of changing everything, LoRA only tweaks a small number of adjustment layers. These layers are much smaller than the original model, so training them is way faster and requires less memory. Basically, it's a really smart way to adapt these massive models without needing to rebuild them from scratch. Okay, let's talk about prompt engineering. It's absolutely crucial when working with these powerful generative AI models. Basically, it's all about how you phrase your questions or instructions to get the best possible results. Think of it as teaching the model exactly what you want. A really vague prompt will likely lead to a pretty vague response, so being specific and providing context can make a huge difference. We'll cover some key techniques like giving clear instructions, supplying helpful background information, specifying the format you're looking for, maybe you want a list or a paragraph, and even using few-shot learning, which means giving the model examples of what you're expecting. Okay, let's talk about how we guide these massive language models. Basically, there are three main ways you can prompt an LLM. That's the instruction you give it. First up is zero-shot prompting, where you just throw a question at it and expect the best it can do based on everything it's already learned. Then we have one-shot prompting, which gives the model *1* example of what you want it to produce, kind of like showing it how you'd like the output formatted. Finally, there's few-shot prompting. This is where you give the LLM several examples of input and the desired output. The more examples you provide, generally the better the results will be, as it gives the model a clearer understanding of your expectations. Let's talk about how we can shape what these AI models write. They don't just pull words out of thin air, they have choices to make at every step. We use parameters like top K, top P, and temperature to guide that process. First up is top K sampling. This lets the model consider only the best candidates for what comes next, creating a shortlist. Higher numbers mean more variety, but can lead to rambling. Next, we have top P, also called nucleus sampling. It dynamically selects tokens until they make up a certain percentage of probability, making sure the output feels natural. Finally, there's temperature. Think of this as controlling how adventurous the model is. A higher temperature makes things wild and unpredictable, while a lower one keeps the responses focused and consistent. Okay, so LLM don't just see words as isolated symbols, they understand them as points in a multi-dimensional space. These points are called embedding. Think of them like coordinates that capture the meaning and relationships between words. When we feed text into an LLM, it first breaks it down into smaller pieces, tokens, and then converts each token into its own embedding vector. These vectors create a rich representation of the input, allowing the model to understand context and make predictions. It's like giving the LLM a map of how words relate to each other. Okay, so while these massive models are impressive out of the box, they're really at their best when you give them some specialized training. Think of it like this: a generalist knows a little about everything, but an expert dives deep into one area. To get an LLM to act more like that expert, we need to fine-tune it. First, you'll collect data specifically relevant to the domain you're targeting, like legal documents or medical reports. Then, you clean and format this data, making sure it's in a way the model can easily learn from. The actual fine-tuning process uses techniques such as low R rate that allow us to adapt the model without needing to retrain it completely. Finally, we evaluate the results and repeat the process until the model performs exceptionally well within that niche area. Okay, let's talk about a really cool trick for getting better answers from large language models. It's called chain of thought prompting. Basically, these AI models are amazing at generating text, but they can sometimes get tripped up with complicated problems that need real reasoning. Traditional prompts just ask the question directly, and the model might give you a correct answer, but without showing its work. Chain of thought prompting is about guiding the model through the steps of the solution. We provide examples in the prompt itself, like demonstrating how to add numbers or break down a problem into smaller parts. This encourages the LLM to mimic that process when faced with new questions. It's like teaching it how to think, and it significantly improves its accuracy and ability to handle more complex reasoning tasks. Okay, let's talk about how different AI models work. There are really three main ways to categorize them: generative, discriminative, and contrastive. Generative models are like creative artists. They learn the patterns in your data and then create entirely new things that look similar. Think of GPT, which can write stories or code based on what it's learned. Then you have discriminative models, which act more like detectives. They learn to tell things apart to classify whether an image is a cat or a dog, for example. Finally, contrastive models are focused on relationships between data points and learn how similar or dissimilar items are. A great example of this would be Clip. It helps bridge the gap between images and text. Okay, let's talk about PEF, that's parameter efficient fine-tuning. Think of these huge LLM like GPT or Llama as being incredibly smart, but also really big. When you try to teach them a new specific task, like writing marketing copy or summarizing medical reports, you often need to retrain those massive weights, which takes a lot of time and resources. PEF is the solution. It's about making these models smarter without needing to change everything. There are different approaches, like low array, which adds small tweaks, prefix tuning, and prompt tuning. They all add just a few extra pieces to the model, allowing it to learn your task efficiently. So, you choose PEFT if you don't have a ton of computing power or memory, or when you only need a bit more performance from an LLM. Okay, let's talk about how we're tackling the tricky problems of hallucinations and bias in these huge language models. These models are incredibly impressive, but they can sometimes confidently make stuff up. We call that hallucination. And because they learn from data, they can unintentionally reflect biases present in that data. The good news is researchers have developed some clever techniques called alignment methods. One popular approach is reinforcement learning from human feedback. Basically, people rate the model's answers, and this feedback helps it learn what a good answer looks like. Another method is constitutional AI, which trains models to follow a set of guidelines or principles. And finally, red teaming involves experts actively trying to trick the model into giving bad responses so we can identify and fix vulnerabilities. While these methods don't solve everything, they've dramatically improved the reliability and trustworthiness of LLM. Okay, let's talk about how these AI models actually get better. It's not just magic. It turns out there are some really interesting rules, or scaling laws, that explain why larger models with more data perform so much better. Basically, the more parameters you have in a model, think of them as little switches, and the more training data you feed it, the smarter it gets. But this improvement doesn't just happen linearly, it follows predictable patterns. We've seen that adding more parameters generally makes a difference, although the gains get smaller as you go bigger. Similarly, throwing more high-quality data at a model consistently helps, though eventually you reach a point where adding even more asterisk data gives diminishing returns. And of course, training these massive models requires enormous amounts of computing power, so understanding how that scales is crucial for designing practical and efficient AI systems. Okay, so these giant models like GPT and Llama are incredible, but training them is seriously demanding. First off, they have an absolutely staggering number of parameters, billions, sometimes trillions. Think about it, each one needs to be stored somewhere. That immediately creates huge memory demands. And not just for storage, the entire model has to be loaded into a GPU memory during training. To tackle this, we use clever tricks like gradient checkprinting. Basically, we recalculate some values during backpropagation instead of saving them all. We also employ mixed precision training, which uses lower precision numbers to save space, but it's important to manage that carefully so accuracy doesn't suffer. Finally, the amount of computation involved is just massive asterisk, leading to incredibly long training times and a huge amount of energy being used, something we definitely need to be aware of. Okay, let's talk about multimodal AI. It's all about models that can understand and use multiple types of data at once, not just text like we're used to with things like ChatGPT. Imagine if you could ask an AI to describe a picture it's seeing, or generate captions for videos. That's the goal of multimodal AI. Models like GPT-4 Vision and Google's Gemini are really pushing this field forward. They've been trained on huge amounts of data that includes images, audio, and video. They use clever techniques, things like cross-attention, to focus on what matters most in each input stream, and fusion layers to combine all that information into a single understanding. It's basically trying to mimic how we process the world using all our senses together. Okay, so let's talk about cross-attention. It's a really clever mechanism inside transformer models that helps them understand relationships between different parts of an input sequence. Essentially, the encoder processes your original sentence and creates a set of keys and values. Think of these as summaries of each word in the sentence. The decoder then generates its output, but it needs to know which parts of the original sentence are most important at each step. It does this by creating queries based on what it has already generated. The cross-attention mechanism calculates how relevant each key from the encoder is to the current query, giving a score for each part of the input. Then, it uses these scores to create a weighted sum, focusing only on the most important parts of the original sentence when generating the next word. Okay, let's talk about making these massive LLM actually usable in real-world applications. The biggest challenge is often the sheer size of these models. They take up lot of memory and require serious processing power to run. That's where quantization comes in. Essentially, it's like shrinking down the numbers that represent the model's knowledge. Instead of using 32-bit floating point numbers, which are super precise but bulky, we can use lower precision formats like 16 or even 8 bits. This dramatically reduces the memory footprint and speeds up how quickly the model can generate text. It's a win-win for efficiency and speed. Okay, let's talk about how we can make these huge transformer models actually work efficiently. The problem is that as transformers get bigger and better, their attention mechanisms grow quadratically with the length of the text you're feeding them, meaning if you double the input sequence, the computation increases fourfold. It quickly becomes impossible to train and run these massive models. Enter mixture of experts, or MOE. Instead of every single token needing to look at every other token, each one is routed to a small group of specialized experts. Think of it like having a team of specialists. Only the relevant ones are consulted for a particular task. This sparse activation drastically reduces the computational cost during inference, while still allowing us to build models with incredibly large parameter counts. Okay, let's talk about how we can make these huge language models actually usable on a wider range of devices. One clever technique is called knowledge distillation. Basically, it's like having a master model, often a really big one like GPT, teach a smaller, more nimble student model everything it knows. The student doesn't just learn the right answers, it learns how the teacher arrives at those answers. This allows us to create much more compact models that are faster and less demanding on resources, making them great for things like mobile apps or edge devices. Okay, let's talk about attention head pruning. It's a clever way to make large language models more efficient. These models use something called attention, which allows them to focus on the most important parts of what they are processing. Inside these attention layers are many attention heads, each learning different relationships between words. Think of it like having multiple specialists analyzing text. Some might be good at spotting connections, others at understanding context. Pruning removes those heads that are really adding much value. It makes the model smaller and faster without sacrificing too much accuracy. It's a balancing act, carefully removing redundant attention heads to improve both speed and efficiency. Okay, let's talk about RAG retrieval augmented generation. Basically, it's a way to supercharge your LLM. You know how LLM like GPT are amazing at generating text, but they only know what they were trained on. RAG solves that problem by giving the model access to an external source of information, like a database or even just relevant documents. It works in 3 steps. First, it retrieves the most helpful pieces of data related to your question. Then, it adds that new info into the original prompt. And finally, the LLM uses both its existing knowledge and this fresh context to craft a more accurate and well-informed response. It's like giving the AI assistant access to a super smart research tool. Okay, let's talk about how these AI models differ. Foundation models are trained on absolutely huge amounts of data, everything from text to images and even code. This gives them a really broad understanding of the world, so they can handle many different tasks without needing much extra training. On the other hand, task-specific models are like specialists. They've been built with a very particular job in mind, and they need a lot more data and effort to become truly good at that single task. Okay, let's talk about something really important: prompt injection attacks. Basically, these are ways people can trick large language models like ChatGPT and others into doing things they weren't supposed to. It's a bit like giving a model an instruction that overrides its core programming. Attackers will carefully craft prompts containing hidden commands, often disguised as seemingly harmless requests. For example, they might ask for a summary but secretly include instructions to print out sensitive data or even run malicious code if the LLM allows it. Understanding how these attacks work is crucial for building safer and more reliable AI systems. Okay, so you've probably heard of LLM like ChatGPT generating amazing text. But how do they actually find the information they need to answer your questions? It's not just about predicting the next word, it's about understanding relationships between concepts. The key is embeddings. Basically, we convert words and phrases into numerical vectors. Think of them as coordinates on a map where similar things are located close together. When you ask a question, the LLM turns that question into an embedding too. Then we store all our relevant documents as embeddings in something called a vector database. Finally, we compare your query's embedding to the document embeddings and retrieve the most similar ones, leading to much better results than traditional keyword searching. Okay, so generative AI models are amazing at creating text, but they're not always right. They sometimes hallucinate, meaning they make up facts. This happens because they're predicting the next word based on patterns in data, not actually understanding what's true. Researchers have developed some clever ways to tackle this problem. One popular method is RAG, which essentially gives the model access to a giant encyclopedia to check its work before presenting it. We also see techniques like fact verification using separate models specifically designed to spot inaccuracies. And sometimes, simply changing how we ask the question, what we call prompt engineering, can help guide the model toward more reliable answers. It's an ongoing process of improvement and a really important area of focus in AI development. Okay, so let's dive into how we train these massive AI models to be truly effective. A really clever technique is called curriculum learning. It's like a smart way of teaching them. Instead of just throwing everything at the model at once, which can be incredibly overwhelming, we start with simpler examples. Think back to when you were learning something new. You likely started with the basics and gradually built up your knowledge. Curriculum learning mimics this process for AI. It involves introducing increasingly complex data as the model learns, leading to faster training, better results, and models that are more reliable, fewer hallucinations or made-up fact. Okay, let's talk about how these massive language models tackle different languages. The secret is actually pretty clever. It's not just that they know a bunch of languages, they understand the relationships between them. First, instead of treating entire words as distinct, they break everything down into smaller pieces called subword units, kind of like building blocks. These blocks are shared across all the languages they've seen. Then, they create this amazing shared space where similar ideas, regardless of the language, end up close together. They start with a ton of training on individual languages and then fine-tune everything using a little bit of multilingual data, essentially leveraging what they've already learned. And get this, sometimes they can even translate between languages without any specific translation examples. It's truly remarkable how well these models have adapted. Okay, so when we're training these giant language models, the ones like GPT or Llama, we run into a serious problem. During the process of figuring out how to adjust those weights to make them better, we need to keep track of what each layer is during its activations. But storing all that information for really deep networks uses tons of memory. That's where gradient checkpointing comes in. It's like a smart shortcut. Instead of saving every activation throughout the entire network, it only saves a few key points. When we go backward to calculate how to change the weights, those missing activations are recomputed on the fly, kind of like refreshing them as needed. This dramatically cuts down on memory usage, letting us train much bigger models than would otherwise be possible. Okay, let's talk about how these giant AI models actually fit into our computers. Because they're so huge, we can't just cram them onto a single GPU or TPU. Instead, they're broken up, sharded. It's like taking a really long book and giving each chapter to a different person to read simultaneously. There are two main ways this happens: tensor parallelism, which splits individual layers across multiple devices, and pipeline parallelism, which divides the model into stages and handles them in sequence. TPU are specifically designed for these kinds of massive computations and often outperform GPU when it comes to LLM. Does that make sense? Okay, let's talk about how we can make LLM generate text much faster. You know, they can sometimes take a while. It's like they're overthinking everything. Speculative decoding is a really cool technique that helps with this. Basically, Instead of having the model carefully consider every single possible word to come next, it makes educated guesses about what asterisk might asterisk be coming up. It's like saying, I think this will probably lead to something good, and then checking if its hunch was correct before committing fully. This clever trick allows LLM to move forward with much greater speed without sacrificing quality. Okay, let's talk about something really interesting: positional bias in transformers. These models are amazing at processing text, but they don't naturally understand the order words appear in. Because self-retention looks at everything at once, it can get confused if you swap two words that are close together. It's like a puzzle where the model needs to be told asterisk where asterisk each piece fits. To fix this, we use positional embeddings, basically little vectors that tell the model this word is here. There's also relative positionals and something called rotary positional embeddings, which can be more flexible. By adding these techniques, transformers are able to really grasp the importance of order in text. Okay, so when it comes to generative AI, we have two main types of large language models: decoder-only models like GPT and encoder-decoder models such as T5 or BART. Decoder-only models are masters of text generation. They're fantastic for things like writing stories, creating code snippets, or building chatbots that can hold a conversation. They essentially predict the next word based on what's already been said. On the other hand, encoder-decoder models are more versatile. They first understand the input sequence through an encoding process, and then use their understanding to generate the output. This makes them really good at tasks like translating languages, summarizing long documents, or answering questions, things where you need a deep grasp of both the source material and what you're trying to create. Okay, let's talk about something really interesting: attention entropy. It's a way to get a little bit of insight into how these massive language models are actually working. Basically, it measures how evenly an LLM is paying attention to different parts of the input text when generating its output. If the model's attention is spread out pretty evenly across everything, we have high entropy. That means it's considering all the relevant information. But if it's focused almost entirely on one small piece of the input, then the entropy is lower, and that can sometimes indicate a less nuanced or potentially more predictable response from the model. Okay, let's talk about something really fascinating: emergent abilities in LLM. These are skills that these massive models suddenly start showing off, like doing complex math or explaining their thinking step by step. It's not like we programmed them to do this, it just seems to happen as they get incredibly large. Basically, the more parameters a model has, think of them as connections in a giant brain, the better it gets at understanding and representing relationships within language and the world. It's like learning from everything you've ever read, but on an unprecedented scale. Okay, let's talk about Autograph, a really cool tool within TensorFlow that lets you use your existing Python code directly inside a TensorFlow graph. Think of it as a translator between the world of regular Python and the world of TensorFlow graphs. Autograph takes your standard Python code, things like working with NumPy or SciPy, and analyzes it, building a TensorFlow graph representing those same computations. It's symbolic execution, meaning it figures out what needs to be done without actually running the code first. Then, it converts that analysis into an optimized TensorFlow graph that TensorFlow can execute efficiently. This is really useful if you want to quickly integrate your familiar Python libraries into your TensorFlow model, speeding up prototyping and potentially even improving performance. Okay, so TensorFlow has a fascinating way it handles calculations. Initially, it used something called graph execution. Imagine you're building with Legos. You plan the whole structure ahead of time and build it step by step. TensorFlow did that too, creating a detailed blueprint first. This was great for speed later on when running in production. But debugging was tricky because errors weren't caught until after everything was built. Then came eager execution, which is like building with Legos. As you go, you see what's happening instantly and can fix mistakes right away. It's much easier to debug, but it can be a little slower. Now TensorFlow defaults to eager execution for the best user experience, but you can still use graph execution in specific parts of your code if you need maximum performance. It's all about choosing the right tool for the job. Okay, let's talk about TensorFlow collections. They are essentially like organizational tools for these incredibly complex generative AI graphs. When you train or run models like GPT or Llama, a huge network of operations is created, kind of like a detailed blueprint of all the calculations happening. TensorFlow collections help us manage this complexity by grouping relative parts of that graph together, things like variables and specific operations. It makes it easier to track down problems, save the entire setup for later use, and even distribute the work across multiple computers if we're training a really massive model. Okay, so when you're working with advanced generative models like LLM, sometimes the built-in training loops aren't quite flexible enough for your specific needs. That's where a custom training loop using gradient tape comes in handy. Essentially, gradient tape lets you record every operation happening during your forward and backward passes. It's like creating a detailed log of everything that happens when your model learns. You start by creating a tape with TF gradient tape, then you define your loss function, compute the gradients using tape gradient, and finally, you apply those gradients to update the model's weights via an optimizer. The code example shows a simplified version. Remember to adapt it to your particular model architecture and loss function. It's all about gaining more control over the training process. Let's talk about control dependencies in TensorFlow. Think of them as a way to tell TensorFlow, hey, don't just run these calculations in any order. I need you to do this asterisk first, asterisk, then that. Okay, let's talk about how TensorFlow tackles non-differentiable operations. Generative AI models are built on these computational graphs, essentially a roadmap for how data flows through calculations. But not every step in that roadmap is easily calculated to measure its impact on the final results. We can't find the exact gradient. That's where TensorFlow gets clever. It uses something called TF function to turn Python code into optimized graph operations and allows us to create custom operators, like sampling functions, if needed. And when an operation really doesn't have a derivative, it employs surrogate gradients, essentially educated guesses about how that part should change during training, allowing the whole model to still learn effectively. Okay, let's talk about a really clever trick we use when training massive models like those LLM, GPT, Claude, Llama, and so on. It's called dynamic loss scaling, and it helps us avoid some serious headaches during the training process. Basically, we're using mixed precision here. That means we're working with both 16-bit and 32-bit numbers. This makes things faster and uses less memory, which is a huge win for these gigantic models. But sometimes, when you do this, your gradients can become incredibly small, leading to vanishing gradients and training problems. Dynamic loss scaling tackles this head-on. It's like having a smart multiplier that adjusts the size of the error signal as it goes through the model. It scales up the loss if the gradient is too tiny, preventing those vanishing gradients. And conversely, it scales down if the gradient gets too big. It's an automatic adjustment based on how things are going, really smart, and keeps training stable. Okay, so TensorFlow is amazing because it can really take advantage of all the processing power available on your computer. But how does it actually do that? Well, think about virtual devices. They are like software copies of real hardware, like your CPU or GPU. TensorFlow operates using these virtual devices, making things much easier to manage. Now, logical device placement is where things get really clever. It's essentially telling TensorFlow exactly which device you want a specific operation to run on. You don't have to worry about figuring out the best hardware for each part of your model. TensorFlow figures it all out automatically based on what you tell it. This leads to some big benefits: faster performance, better control over resources, and the ability to easily switch between different devices if needed. Okay, so we're talking about a clever trick called graph kernels. Basically, they're like shortcuts for TensorFlow. Instead of running the whole model every time, these kernels use mathematical functions to quickly estimate how similar data points are. It's all based on the structure of the data. Think of it as looking at relationships between things rather than just individual values. TensorFlow uses this internally, especially when dealing with really big datasets or complex models, leading to a significant speed boost and reduced memory usage. Okay, let's talk about saved models. Basically, they're how we package up our trained generative AI models so we can actually use them in a real-world setting. It's like taking a fully baked cake and putting it in a box ready to serve. Inside each saved model directory, you'll find several key folders. The variables/folder holds all the learned weights of your model. Those are the numbers that define how it works. The checkpoint/folder is for saving snapshots during training, so if things go wrong, you can easily pick up where you left off. Then there's the config/directory. This is super important. It contains the blueprint of your model, how many layers it has, what type each layer is, and all those other details. Finally, sometimes there's an assets/folder for any additional files that the model needs. Okay, so when we're building these massive generative AI models like GPT or Llama, they need tons of data. That's where TensorFlow datasets comes in. Think of it as a really well-stocked warehouse of datasets ready to be plugged into your training pipeline. It's part of the TensorFlow ecosystem, and it simplifies things massively by offering pre-cleaned, formatted, and standardized datasets. You don't have to spend ages prepping them yourself. There's a huge variety available too, from images like the ImageNet dataset to text corpora. And because they're designed for TensorFlow data pipelines, you can get everything running smoothly with minimal effort. Okay, let's talk about how we can make processing variable length sequences more efficient when working with powerful models like transformers. The key here is bucketing. Imagine you have a huge dataset of text where each piece of text has a different number of words. Directly feeding all these different lengths into our model would be really inefficient, both in terms of memory and training speed. So, we group similar length sequences together. Think of it like sorting students by their grade level. We create buckets based on the length of each sequence. Once we've done that, we can treat all the sequences within a single bucket as a uniform batch, which TensorFlow can process very quickly and efficiently in parallel. It's a clever trick to optimize our training workflow. Okay, let's talk about a really crucial part of training these huge AI models: dataset prefetching. These LLM like GPT and Llama need tons of data to learn effectively, but if we just load it as we go, it creates a major bottleneck. Prefetching is the solution. Essentially, we're proactively loading chunks of the dataset into memory before the model needs them. This dramatically cuts down on wait times for the GPU, speeds up training iterations, and helps keep things running smoothly, preventing those frustrating fluctuations in batch sizes that can mess with the learning process. Tools like PyTorch and TensorFlow have built-in features to make this happen efficiently, often by using multiple worker processes to overlap data loading and computation. Okay, let's talk about how TensorFlow handles training these huge language models. Because LLM or massive asterisk, they simply won't fit on a single computer. It would take forever and require way too much memory. So, we need to distribute the work. The core idea is that we split up the data and then combine those results. Essentially, each device gets a piece of the training set, calculates its own gradients, and then TensorFlow figures out how to bring all those gradients together efficiently. A key technique here is called reduce, which is like a super fast way for all the devices to share their calculations without constantly sending data back and forth. And thanks to NVIDIA's NCCL library, this reduce happens really well on NVIDIA hardware. Okay, let's talk about how TensorFlow tackles big training jobs. When you're dealing with massive data sets and complex models, running everything on a single machine just isn't feasible. That's where distributed training comes in, and that's where the coordinator steps up. Basically, the coordinator is like the brains of the operation. It breaks down your training task into smaller chunks and assigns them to different worker machines. It keeps an eye on those workers, making sure they're all running smoothly and collecting their results. Then, after each mini batch, it combines everything and pushes updated model parameters back out. It's all about keeping the whole process synchronized and consistent across the entire distributed system, a really clever way to speed things up. Okay, So when we're training really big AI models like those transformer networks and LLM, they can eat up ton asterisk of memory. Specifically, the gradients which tell us how to adjust the model's weights need to be stored during backpropagation. That means keeping track of every single intermediate value calculated in each layer. It's like building a massive chain of calculations and having to remember every link along the way. Gradient checkpointing is a clever trick that allows us to avoid storing all those activations in memory at once. Instead, it only stores them when they are actually needed during backpropagation. Basically, parts of the calculation are skipped and then recomputed on demand. It's like saying, I don't need to remember this step right now. I'll handle it later. This reduces our memory usage significantly, letting us train models that would otherwise be impossible, but it does come with a slight increase in training time because we have to recalculate those steps. Okay, so when we're talking about the really huge generative AI models like GPT or Llama, they're just massive asterisk, right? They have billions, sometimes even trillions, of parameters. That means they need a ton of memory to run, and often one single GPU won't cut it. That's where model sharding comes in. It's basically like splitting the model up into smaller pieces so you can fit them onto multiple devices, usually GPU. TensorFlow makes this super easy with its TF Model Parallel API, letting you divide the model and distribute the computations across those devices. You can even split individual parts of the data. It's a clever way to tackle these giant models and make training and deployment possible. Let's talk about getting our TensorFlow models running smoothly on edge devices, things like smartphones or smaller computers. That's where TensorFlow Lite comes in. It's a really clever system that makes it possible to run these powerful models without needing tons of processing power. The process involves a few key steps. First, we need to optimize the model itself by reducing its size and precision. Then TF Lite transforms the original TensorFlow graph into something more efficient for edge devices, and finally it generates custom code specifically tailored for that device. Okay, let's talk about model pruning, a clever technique to make these massive AI models more manageable. Basically, we're streamlining them by removing less important parts. Think of it like trimming the fat off a really big tree. You still have a strong shape, but it's lighter and easier to work with. TensorFlow provides tools for this using structured or unstructured pruning methods. Structured pruning removes entire groups of neurons or filters simpler and often faster on newer hardware. Unstructured pruning targets individual weights based on how much they contribute, offering more flexibility but potentially requiring some extra effort to fully leverage the speed improvements. The toolkit helps you train with quantization in mind too, ensuring your prune model works efficiently. Okay, so let's talk about how we make these massive AI models run faster and use less memory. One key technique is called quantization, essentially shrinking the size of the numbers representing our model's weights and activations. We have two main approaches, static quantization and dynamic quantization. Static quantization is like setting a fixed bit width, say 8 bits for asterisk everything asterisk. It's simple to implement and gives you a nice performance boost, but it can be inflexible if your data changes during use. The accuracy might suffer. Think of it like using one size shoe that doesn't fit perfectly. Dynamic quantization is more intelligent. Instead of predefining anything, it figures out how many bits each number asterisk needs asterisk at a specific moment while you're running the model. It adapts to the data. It's a bit more complex to set up, but generally results in better accuracy and avoids those size issues. Essentially, static quantization is like having a fixed shoe, while dynamic quantization is an adaptive one. Okay, let's talk about keeping those massive models from running out of memory. LLM like GPT and Llama are huge consumers of RAM, specifically GPU memory. When you try to run them in TensorFlow, you might get an out-of-memory error, which is a real headache. TensorFlow has a handy tool called tfconfig experimental enable memory growth. Essentially, it lets the GPU dynamically expand its memory during runtime. However, it's not magic. You need to set a maximum limit for how much growth is allowed. Think of it like saying, Okay, you can borrow some extra RAM, but don't take all of it. Using tfconfig experimental set memory growth lets you define that limit, typically in gigabytes. And remember to monitor your GPU usage to make sure everything's running smoothly and not getting dangerously close to the limit. Okay, so let's talk about tensor arrays and TensorFlow. They are basically containers designed specifically for handling sequences of data where the length isn't fixed. Think sentences that can vary in size. Traditional tensors have a set shape, but with models like LSTMs and transformers, we often deal with variable length inputs. Tensor arrays solve this by letting you build up a sequence dynamically, making them super useful for RNN and transformer layers. They're more efficient than constantly creating new tensors as the sequence grows, which can really speed up training. Okay, let's talk about debugging slow TensorFlow data pipelines, a really common challenge. The first step is always to figure out where the slowdown is actually happening. Don't just guess, use tools like TensorBoard and TF Profiler. These give you incredibly detailed information on everything from CPU and GPU usage to exactly which operations are taking the longest. Once you've identified those slow spots, it's time for some code inspection, looking at your data loading, preprocessing steps, and even batch sizes. You can also use TensorFlow's built-in debugging tools like TF debugging checkup to spot any unexpected behavior. Finally, don't just optimize once. Continuously monitor your pipeline's performance as you make changes, and keep refining it until it runs smoothly. Okay, so when we're working with large language models and the data they're trained on, like text, it often isn't perfectly uniform. Think about how sentences have different lengths. Regular tensors are nice and neat, all rows having the same number of columns. But real-world text doesn't do that. That's where ragged tensors come in. They're essentially a bunch of smaller tensors, each with a different size, combined into one structure. They use more complex indexing to grab specific parts, and can sometimes be a bit less efficient for certain calculations because they aren't stored contiguously in memory. But this flexibility is crucial for LLM, allowing them to handle sentences of any length without having to pad or truncate everything. Okay, let's talk about avoiding overfitting in our generative AI models. Overfitting happens when your model gets too good at the training data. It starts to memorize the noise and specific details instead of learning general patterns. A great way to combat this is with early stopping. Early stopping is like a smart pause button during training. It monitors how well your model performs on unseen data, specifically the validation set. If we see that the performance and the validation set starts getting worse, meaning it's overfitting, then the training process automatically stops. This saves us time and resources, and more importantly, it helps our models generalize better to new, real-world data. We can configure early stopping by setting parameters like how much improvement is needed before we stop min delta and how many epochs with that improvement will wait for patience. Finally, we make sure to restore the best weights, the ones that performed the best on validation, so our final model benefits from what it learned. Okay, let's talk about multitask learning. It's a really clever technique for improving generative AI models. Basically, instead of training a separate model for each task you wanted to do, we train one single model to handle several related tasks at the same time. This can lead to better generalization, meaning the model will perform well on new data even if it hasn't seen it specifically during training. It also helps when you don't have tons of labeled data for each individual task. By sharing knowledge between them, the model learns more efficiently. TensorFlow makes this pretty easy through shared layers, adjustable task weights to prioritize what matters most, and using loss functions combined in a weighted way during compilation. Think about an LLM that needs to both summarize text and analyze its sentiment. Multitask learning helps it master both skills effectively. Okay, let's talk about fine-tuning pre-trained models. It's a really smart way to get great results without needing to train an AI from scratch. You start by picking a model that's already good at something related to your goal, like BERT for text tasks, and then load it using TensorFlow Hub. Next, you need to make sure your data fits the model's needs, which often means preparing it in a specific way. Sometimes, you might even add a small layer on top of the base model if you need a particular output format. Finally, remember to use a really low learning rate during training. We're just nudging the model a little, not completely rebuilding it. Okay, let's talk about how TensorFlow and PyTorch actually run your machine learning models. Historically, TensorFlow used something called a static graph. Think of it like creating a detailed blueprint before you start building. You define the entire process up front, all the calculations, layers, everything. This lets TensorFlow do some serious optimization for speed, especially when deploying to production. However, this could make debugging tricky because you're not directly interacting with the model as you run it. More recently, TensorFlow has embraced eager execution, which is much closer to PyTorch's approach. Now, let's move on to PyTorch. It uses a dynamic graph defined by run. Basically, you define your computation step by step as you execute the code. This makes things a lot more flexible and intuitive. You can easily debug because you can just run through your code line by line like normal Python code. It's often felt as more natural for people who are used to programming in Python. Essentially, TensorFlow prioritizes optimization and deployment, while PyTorch emphasizes flexibility and ease of use. Both have their strengths. Okay, so you've got your amazing generative AI model, maybe a super smart chatbot or an image generator. But running it for millions of users isn't simple. That's where TensorFlow and Google Dataflow come in. TensorFlow is the tool we use to actually build these models, training them on huge amounts of data. Now getting that model into action at scale needs something more robust, and that's where Apache Beam and Dataflow shine. Think of Beam as a common language for describing how you want your data to be processed, cleaning it up, formatting it, feeding it to the model, and then taking whatever the model spits out and sending it back to someone. Google Dataflow is a managed service built on Beam that actually does all that processing in the cloud, handling the scaling and making sure everything runs smoothly. It's like having a super efficient data factory behind your AI model. Okay, let's talk about how we can help models understand longer relationships within time series data. A big challenge is that many traditional models can only see a limited amount of past information. They have a fixed input length. Dataset windowing solves this problem by essentially creating multiple overlapping snapshots of the data. Think of it like sliding a window across your time series, capturing different segments at once. We can look back, focus on the present, or even peek into the future to make predictions. It's a clever way to trick the model into recognizing patterns that would otherwise be hidden by that length limitation. This is really useful for things like predicting sales trends, spotting anomalies, and even analyzing financial markets. Basically any situation where understanding how past events relate to the future is crucial. Okay, let's talk about multi-label classification. It's a common scenario where something can belong to more than one category, like an image that contains both a dog and a cat. We use sigmoid activation in TensorFlow for this. The sigmoid function gives us a probability score between 0 and 1 for each possible label. So, if we set a threshold, say 0.5, then if the probability of a particular label is above 0.5, we assign that label to the item. We use binary cross-entropy loss because each label is essentially treated as its own independent binary classification problem. Let's talk about TensorFlow probability, often called TFP. It's a really cool addition to the TensorFlow ecosystem. It's specifically built for handling probability and uncertainty. Unlike regular TensorFlow, which is great at precise calculations, TFP lets us work with things like random numbers, different distributions of data, and even incorporate our own knowledge or assumptions into models. You'd really want to use TFP when you're building Bayesian neural networks, generative models where randomness plays a role, or simply when you need a more robust way to understand how confident your model is in its predictions. It gives us tools for representing complex probability distributions that go beyond what we can easily do with standard TensorFlow. Okay, let's talk about how TensorFlow handles text in its models. When we feed different lengths of sentences into a neural network, and that's common with things like transformers, we run into a problem. All the matrices need to be the same size. So TensorFlow uses padding. Padding adds special tokens, often zeros or a specific PAD symbol, to shorter sequences until they match the length of the longest sequence in your batch. But here's the trick: we don't want the model to learn that padding asterisk is asterisk actually part of the data. That's where masking comes in. A mask is like a little flag telling the network which parts are real words and which are just padding. TensorFlow makes this really easy with functions like pad sequences. You can easily create a mask, usually by using the bitwise not operator to invert the padded positions. Okay, let's talk about activity regularizers in TensorFlow Keras. These are a really handy tool for stabilizing your training process, especially with larger and more complex generative models like those built using transformers or LLM. Think of them as encouraging the network to produce more consistent, predictable activations, basically preventing wildly fluctuating output values. They work by directly penalizing the magnitude of these activations within each layer. You can implement this using lone or L2 regularization specifically applied to the activity, and Keras makes it super easy through its activity regularizer argument in your dense layers. The code example shows how simple it is to add this to a sequential model, letting you control the strength of the regularization with a hyperparameter like 0.1. Adjust that based on your specific dataset and model needs. Let's talk about how Keras functional API models work. Instead of just stacking layers one after another like you do with a sequential model, the functional API lets you think of each layer as its own independent function. This makes it super easy to build really complex architectures and reuse parts of your model in different ways. You define input and output layers, then use decorators like a TF Keras layers dense to create connections between those layers. It's all about defining how the data flows through the network, and that flexibility is a huge advantage when you're tackling challenging problems.